Oh. Any volunteer, or we can name? No? Clarence, your first one with starting with C, so
Yeah, okay.
go for it.
Co-host.
Yep. Just
yeah.
Okay. Yep. So can you see this?
Yes, we can.
All good? Okay. All right. So hello, my name is Clarence. So my project is exploring driving behavior in Australia. So my supervisors are both Simona and Tuo. So just as a recap on the project from last semester, so this project examines driving incidents using data from Compass IoT. So in this data set, we have like driving incidents, which mainly are captured from New South Wales, but there are some incidents which are captured from like maybe Queensland as well. So yeah, last semester, what I did mainly was conducting data analysis and data mining on the data set. So I did a lot of data visualizations and a lot of graphs. Yeah. So near the end of the semester, I started creating like the methodology for using machine learning algorithms on the data set. So this semester continues with some more data analysis and data mining along with the machine learning. Yeah. So this semester I did some of these so we had to decide for the machine learning, we had to decide what were we going to be predicting. So what I wanted to do was to figure out if I wanted to predict the number of incidents in each LGA by maybe date, by the per day or per week or per month. And this visualization, I did it on the top 2 LGAs, which had the most incidents in New South Wales. Yeah, so in the in the graph for per day, we can see that there's like a common trend, I guess. But for per week and per month, I guess like there's not really like a trend that occurs. So for this, we decided to choose to predict the number of incidents in each OGA per day. Yeah. So this, I also did like a box plot. So this was per every weekday. So we can see that there's like, we can see there's some outliers, I guess, per day. But besides that, yeah, like there's, yeah, we can just see like there's incidents occurring in each day. I guess some days have more incidents occurring, but some days have less. So like we can see that on both of these for Parramatta and CBD, we can see that Sunday has like the least amount of incidents occurring. Yeah. So just continuing on. So I also did this histogram plot graph. Yeah, so this was the incidents per day of the top 10 LGAs. So we can observe that despite not being like the top LGAs that have the most incidents, they still all follow the same trend, which like peaks around like this specific one point. Yeah. So now moving on to the machine learning methodology. So like I said before, this model, we're trying to create a machine learning model which will predict the number of incidents in a single day in an LGA. So these features in the machine learning model will include data from the dataset and also the demographic data from the 2021 census data. So since we're predicting each the number of incidents in an LGA, we can just import the demographic data in that specific LGA. So using this data set, we will be splitting it into a 70-15-15 split. So 70% of the data will be put into training, 15% will be put into testing, and 15% will be put into validation. So far, at this stage, we're testing only 3 models at this point of time. So preliminary testing will only include, we're currently using Random Forest, XGBoost, and Light GBM. So the results from these 3 models. So we use 3 different statistics for this. We use the R-square, the RMSE, and the MAE. So for random forests, we achieved an as a result of 0.649. With RMSE, we got 14.723. MAE, we got 4.504. For XG boost, we got 0.652. For RMSE, we got 14.662. MAE, we got 4.537. For light GBM, we had 0.668 for R square, 14.308 for RMC, and 4.369 for MAE. So from these results, we see that light GBM was probably like the most performing algorithm out of these three. It did have like the highest R square and also the lowest errors for RMC and MAE compared to the other two models. Yeah. The second best was probably XG boost as well, just because it had less higher R square and lower error for RMC than random forest. Yeah. So this was, I also plotted the predicted and versus the true values for all three models. So a common thing that we can observe in all three results is that none of the models were able to predict like the outliers. So any values that had above 300 incidents in a single day, none of the models were able to predict that. But yeah, besides that, I think we can see that the models did perform somewhat okay, at least for initial, this is preliminary testing still. So we still have a lot of improvements in these models. Yep. So for future work in the future, so what I would try to do would be removing outliers from the data set. So maybe removing the points where there's incidents, where there's more than 300 incidents in a single day. Also, another thing to consider was to do hyperparameter optimization. So using the validation data set on each of the models. So maybe we could produce like better results from each of the models. One more thing that we could have done was use the most important features only in the models. So in this data set, we had a lot of features. I believe there was 10,000 features in our machine learning model. So one thing that we could improve on each of these models was to use maybe only the top 100 features only. Another thing to do in the future is compare between more machine learning models. So right now I'm thinking of using these machine learning models. So gradient boosted decision trees, support vector machines, linear regression, k-nearest neighbors. Another thing to consider right now, this machine learning problem is currently a regression problem. So we're predicting the number of incidents in each LGA per day. But one thing we could consider is changing this problem to become a classification problem. So maybe we could have different classifications of number of incidents. So maybe an LGA on a certain day may have low incidents. So maybe under 10 incidents per day. Maybe there might be a medium number of incidents. So maybe like 10 to 100 and a high number of incidents. So greater than 100. Yeah. Another thing we might do in the future is clustering of driving incident points. So just clustering incident points by geospatial. Yeah. And that's the end of my presentation. Yep.
Thank you, Clarence. Feel free to ask your questions via chat. And one thing you didn't present for people is your feature ranking, which was super funny. I would have actually added that.
Yeah.
Do you want to share maybe a few words about it?
I'm not too sure.
Okay, that's fine.
Yeah.
He also did a feature ranking of each models, and there are some very interesting population demographics that lead to the apparition of risky driving behavior. I think he might present that in the final presentation so we can all have a good laugh about it. But of course, demographic data can actually say a few words about what neighborhoods are driving badly or not. Okay, good. Thank you. Tuo, looking for our next speaker. Anyone wants to volunteer or? Do we make a lucky guess? Okay, then maybe we move to Yohanes.
Yep, okay, wait a second, please.
Yeah, let me just give you the co-host. Yeah. Yeah. You're okay to share your screen.
Okay, could you see my screen right now?
Yes.
All right. Good afternoon, everybody. Today I will bring some presentation about report and finding about Victorian train. So the current analysis will about like the whole. In the previous presentation, I only brought like only the particular line, but in this occasion, I will bring some analysis about the whole analysis, the whole lines. Okay, before we are going to the gist of the topic, so the off-peak distorted discount fare in Melbourne is applied when we leave or arrive in Melbourne between like 9 in the morning and 4 in the afternoon, and then leave or arrive in Melbourne after 6 p.m. on weekdays, and it is also applied on weekends and public holidays. And then peak hours is applied when on like 7 until 9 a.m. and 4 until 6 p.m. So the first section is about overview analysis. This is the period of observation. And then we can see that during 2019, like between 7 until 9 a.m., there is a peak AM, and then from 4 until 6 p.m., there is a peak on PM hours. So from the sample that we take, like February and then March, between 2019 and 2021, there is no difference between the peak hour. So like in the 7, 8, or 5 and 4 and 5, there is a peak hour. So the peak hour didn't shift into another time or another hour. Same thing also happened in August and November. So in 7 until 9 for both months, both also happened in 2019 and 2021. The peak hour in the day still on like 8 and on 5. There is no shifting in the peak hour. So yeah, this is the monthly analysis recap. There is no shifting in travel pattern. This is the yearly analysis. So we describe like how many the decrease of the patronage capacity, like most of all, because maybe COVID and another situation, like from the sample like drop around like 60% and more. Especially on this PM peak, the decrease is a little bit different from EM and PM. So I think it's a little bit lower than the EM. So this is the number of patronates, the yearly analysis. So we take the 5 busiest station. So we realized that this 5 station has the big patrons because like all of lines like stop in this station, like Flinders Street, Southern Cross, Richmond, Melbourne, and Parliament. So this is the comparison between 2021 and 2019 for the 4 busiest station. And then this is the factor affecting patronage demand, like hygiene and crowd concern, strict traveling, and then the policy of work from home. So this is the discussion, like the same thing. The pattern between 2021 and 2019 is the same. So there is a decrease in patronage because of like health concern and some policy. And then the second section is about time series forecasting. So this is the time series forecasting. So I only take the 2019 sample, but I realized that we need some more sample to analyze, because like if we see the RMSE test number, it still has the big number. So it concludes the bad training, but it has several factors, like maybe because we only have like limited number of sample, so the machine learning cannot like learn the pattern properly. So in this slide, we use like fine tree and Armachern 5.2. They still like have the high RMSE number, because yeah, there is a bad training, but I realized that we have only limited number of sample. So I also use like boosted trees, but it also has the high number of RMSE, so it figure like the bad trainings model, like maybe because like limited number of sample. So because like there is a lot of problem in training and then that data set, so the future improvement, we want to like improve our data quantities, like maybe we improve the number of weekly analysis. We only have 8 weeks, so hopefully we can get like 1 year analysis, so we can get a lot of data. And then we also like decide what validation method that we want to use. And then we want to increase the training and prediction horizons, include sensitivity tests. Yeah, that is all from my presentation. Any suggestion or question?
Thank you very much. It's good presentation.
Thank you, Yohanes.
Yeah, thank you.
Any questions, feel free to ask in the chat for Yohanes. And don't be afraid to ask them if you've noticed something that looks, a little bit different to you. We can move to Minwei.
Yes. You guys can see my share screen. Okay, start. Hello everyone, my name is Minwei Chen. My research project name is Impact of Electrical Vehicle in Transport and Energy Mobility. Today I will present from 4 aspects: project discussion, data connection, and modeling most, and future work. For the last semester, I do the literature review, and for the literature related to electrical vehicle, in terms of the transport, with the increasing of the number of the charging station, electrical vehicle will replace the traditional vehicle. Increase in the penetration rate of the electrical vehicle will lead to congestion in some charging area. However, in terms of energy, large-scale charging of the electrical vehicle will need to many unstable factors in urban power grid, which will lead to the grid overload. Therefore, the impact of the electrical vehicle on transportation and the power grid should be analyzed. And some factors such as the location, penetration rate of the electrical vehicle, and the state of the power grid should be considered as well. In the recent research about the impact of electrical vehicle on traffic, have focused on the charging station to reduce congestion. While current research into the impact of electrical vehicle on grid is focused on the electrical vehicle scheduling and the new energy generation to reduce the peak hour pressure. Therefore, lack of the quantification of the impact of electrical vehicle means the electrical vehicle penetration rate Therefore, this study will model according to the current transportation system to practice the impact of the recent electrical vehicle on transport in the future. This research project will solve the next problem, impact of the electrical vehicle on transport under the different state of charging, and the impact of different penetration rate of electrical vehicle, and simulate the battery consumption and of electrical vehicle in different penetration. I will use the simulation through the Amazon. For this semester, I do the data connection. I will connect some information about the electrical vehicle and add the electrical modeling in Amazon. Based on data from Electrical Vehicle Council and the Australia Bureau of the Statistics in 2022, the sale of electrical vehicle will treble compared with the previous year, accounting the 2% of the all sale. The report also discussed the current state of charging limits for electrical vehicle. Since the technology of electrical vehicle cannot accommodate power supply that some fast charging can distribute. Recently, there are 291 public fast charging stations in Australia, and it is estimated that 700 charging stations will be built in the next 5 years. However, in the Sydney, New South Wales, the area where the most electrical vehicle is Davis Point, Haymarket, Mears Point, and the Rocks. According to for the 0.54% of the all vehicle in this area. Therefore, when modeling the analyze the impact of electrical vehicle, I will model from different electrical penetration, namely 0.5%, 1%, 2%, even 10%. Visualize the impact of electrical vehicle as a macroscopic model, which can more easier to show the impact of the electrical vehicle on traffic. In addition, the Electrical Vehicle Council also shows the survey in 2022, in which the 714 response will ask to find the common 12 hours charging time in 40 hours for 24 hours. For this same time period of the electrical vehicle simulation, I will base on the two peak in the data, midnight and noon. So which means I should do the simulation from the 12 o'clock to 2 a.m. and 12 p.m. to the 2 p.m. For the modeling modes, I will use Amazon to combine this project. Based on the calibrated Amazon model, I will use the macroscopic free flow acceleration model and the battery consumption model for electrical vehicle, and streamlined energy consumption and estimation model. For macroscopic free flow acceleration model and battery consumption model for the electrical vehicle. First, I need to add electrical vehicle categories to the model, and I will add them to the model according to the electrical vehicle penetration. Like I mentioned before, the 0.5 and 1 or 2%, and I will create a different scenario for this modeling. And next, I will base on the power type of electrical vehicle by Amazon. The battery consumption of electrical vehicle and their battery capacity should be analyzed, which means the different vehicle attributes will be considered. Therefore, the battery consumption statistics can be generated from the network, each the road section, the turn, and the subsection. The energy and the battery consumption model can be visualized the battery consumption in this network. At the vehicle level, the current charging state of charging, the battery current consumption that in the dynamic simulation modeling. In addition, energy consumption and the battery models can be used to enable the vehicle by energy type or current state of charge. The model output of the sample is shown is 2 finger. I will simulate the energy of the battery consumption model of the electrical vehicle in my future next work. For my next half semester, I will finish my Emerson modeling, include the calibration of the Emerson and add the electrical vehicle impact of the modeling. And I will to output macroscopic free flow acceleration model and battery consumption model. Means I will get some result for my research project. And I next will to check my results and to do some finish my final report. Okay, thanks everyone. Does anyone have any question?
Thank you, Minwei.
Okay, thank you so much.
You can type your questions in the chat and then we'll discuss at the end. In the meantime, we can continue with Rheshav on my list.
Sure. Just confirming you guys can see that.
Yep.
Okay, awesome. So kicking off, my project is on explainable AI in intelligent transport systems. First off, we will go over the agenda, which is we have our introduction of the topic, getting more into the research topic, then going over a review of the research that was done up till this week or this first half of the semester, then analyzing those findings and then trying to outline next steps for not only this project, but in an overall sense of the space as well. So first, we have an introduction. You will see that over this entire presentation, there's going to be references to explainable AI, and also trying to make AI more ethical, making it responsible for the application of intelligent transport systems. And that will be covered by a research snapshot, just a summary of the details that I have gathered over the past few weeks. And as a recurrent topic over the presentation, you'll notice about the impacts of explainable AI on current AI systems within intelligent transport systems, as well as the impact it can have on future systems. So first off, the research topic, explainable AI in intelligent transport systems. Explainable AI essentially focuses on the development of human interpretable systems to assist in the understanding of how an AI system operates. You'll see that over time, there has been an increasing need for explainable AI techniques so that we can develop more safer, more responsible systems within intelligent transportation. And then that raises the question as to why we need to develop such systems. That leads us to the problem, which is we have systems in place right now, which are pretty much defined as black box systems. They don't have a lot of explanation. They don't have any sort of detail on why some decisions are chosen or why the model tries to select a certain output. So therefore, there's a need for research and development into these systems and trying to understand them on a pseudo-molecular level. And by doing that, we want to shift this negative perspective that a lot of people have on simply machine learning and AI. Of course, we all see in movies about all the terrors of AI, but we want to try and understand that on a more philosophical level and try and apply it so that it's more helpful, not only for the general public, but for us as researchers and developers as well. Then we have a review of the current state of the AI systems. You'll see there's a lot of optimization-based models being in use for current systems. These include genetic algorithms, simulated annealing, fuzzy logic models, and colonizer optimizer. And colony optimizer. Most of them I have found to be used in more low-risk applications, which are traffic management or traffic predictions, mapping, and just on a higher level in terms of intelligent transport systems, not quite into the autonomous vehicle realm, as one would say. Then, of course, there's a limited understanding of these systems within transport. Hence, that warrants the need for research into it. And a thing about our studies is that while we have all this data available, we are jumping into the ethical problem of whether this data that we've aggregated was done in an ethical way. Does it respect privacy concerns? Does it respect data integrity? And that's where ethical discussions delves deeper into whether there's an oversight on the type of data being used and the type of models being built for intelligent transport systems, because the main concern is safety. A study by Arun Das and Paul Rad also mentions that as the complexity of an AI model increases, there's a proportional decrease in its understandability, which is a common theme you'll realize as I go over this presentation, is as I discuss more complex algorithms or more complex implementations, you'll notice that there's much less research or understanding of how these systems work. These branch off into three main concerns, which are the current efforts. So this is for research. We have the current efforts, what kind of systems are in place to make more explainable AI models, or can we make current AI models more explainable? And then we have the ethical concerns, which also deal with the current efforts, as it kind of drives the conversation in terms of the discussions within ethical concerns. Is like, we want to worry about safety, we want to worry about the risk factor, and we want to understand how these systems work. And that drives the conversation towards building an effort to hybrid systems and adapting tools to make current systems more explainable. And a very outstanding point that I found was model-specific explanations. So in the realm of intelligent transport systems, we want model-specific explanations, because we want to be able to understand the specific use cases and understand what decisions are being taken within the model for that specific use case. Then we have the metrics. How are we calculating the explainability of an AI model, right? So we have the SHAP value, which uses game theory to try and understand or try and break down the overall decision into probability-based smaller features, so that you can understand which features had the most effect on a certain decision. Other ones we can see are residual plots, class prediction errors, and model performance metrics, which are just general accuracy-based metrics. Then coming down to the divisions of explainable AI and the research according to it, is we have our autonomous transport division, which purely deals with autonomous vehicles, electric vehicles in use today. Think Tesla and their autopilot system. Public transport systems, such as managing them, which also bridges with the management side of the division as well. And then computer vision and LiDAR-based systems. So trying to build an autopilot system, essentially, if you were to put it in a use case. We have the ethical research. Given the nature of this entire field, we want to promote safety. And a very important point was the ethical development of AI. So we can have ethical AI, but what about the development? It starts there. So that's one of the main points that they mentioned there. And of course, going into more detail is sustainable transport. How sustainable is how can we make transport more sustainable using AI, trying to make it more understandable, trying to make it more efficient, and making sure that we have the environmental impact in mind as well. My project will be more focused in the modeling and analysis division, which goes into specific use case of incident detection and prediction, which will be further discussed. Then we have the findings. This is on an overall scope. We have research gaps regarding the development of explainable models, the lack of ethical definitions, as well as complex model analysis. So this is when we have deep neural networks and we're trying to explain that, but at the moment it's much more difficult, hence the need for explainable AI development. Right now we have hybrid examples, model agnostic or specific explanations. Like I explained before, we can either have a global explanation for a model, or we can make it very specific to the specific use case. And then that we have decision tree algorithms to explain the if-then logic of deep learning models, which will be further discussed. There's a very important, or rather paramount, research that I found regarding prototype explanations later on in the next 2 slides. IBM also claims that there can be an up to 50% reduction in model monitoring effort by developing explainable AI at the core, and up to 30% increase in accuracy of models. So from research, I've found that by making a model more explainable, we're able to analyze the type of decision it takes and try to improve upon all those decisions, because we can understand why it took these decisions, and then try and lead the algorithm in a way that is more desirable. You will also notice combined models. There have been studies where combining models have garnered higher results or a higher reliability in the decisions it's taken, which has been very helpful in terms of incident detection, because there's a lot of features involved in it. This is the evaluation criteria. I'm very happy to come back to it later, but as I am a bit pressed for time, I'm going to skip ahead to the next one, which is the transport incident analysis. So the models used here are support vector machines, feed-forward neural networks, convolutional neural networks, regressions, and decision trees. On the right, you'll see a diagram, which pretty much goes back to when I mentioned the prototypes and explaining a certain result with prototypes. So essentially what this proposed framework does is it models the if-then rules onto a prototype layer, which exists as a precursor to the output layer. The prototypes are selected data samples within the test dataset, which the user can view and map out the if-then logic processes which were involved in making a single decision. Another proposed frameworks you will see is the VNS-based explainer, which is a variable neighborhood search. This essentially tries to identify the most meaningful features within a data set, and then tries to rank them so that it makes more sense to users as to why this decision was taken. So it tries to prioritize features and tries to give you an understanding of this feature had the most effect on the decision. There is one research gap here. There's a lack of sufficient tools and models that can better interpret deep neural networks. But this diagram here, or this study here, pretty much gives a very positive outlook as to a step towards filling that research gap. The next steps is to develop explainable AI into low-risk transport systems. So while we may have black box systems in low-risk transport systems, we want to make them more explainable or develop something for low-risk transport systems so that we can support our decisions, support our models, and try to improve upon them before going into high-risk applications, which have much more higher safety concerns. And the ethical considerations to take here is to define clear parameters of safety and enforcing the explainability, especially in high-risk applications, and then as an overall effort to define ethical guidelines, not only on the project level, but on a more larger scale for the entire space. And finally, for any model specific considerations, we want to approach machine learning models with an explainability mindset. So trying to prioritize explainability and safety, especially inside of the intelligent transport systems. And then go into ethical development processes so that we don't have to worry about developing something and then worrying about the ethical implications later. And then employment of hybrid explanation methodology. So this is on this diagram here, you'll see that we are already developing a model, we evaluate it, and then we explain that model before we produce a final output. And then there's a research gap, which I think I want to explore, is trying to use machine learning to explain existing models. So it's kind of like a deep inception into machine learning to explain machine learning, but that's something I want to try and do much more research into and see if it is even possible at this stage. And as a summary, the road to ethical and explainable AI in ITS, exploring explainable deep neural networks on higher risk explanations will help us understand where we can take explainable AI and how far we can take it before we reach an ethical barrier. And then building universal explainable techniques. So this is for rather a model agnostic global explanation. And then developing guidelines, ethical guidelines based on safety concerns, based on the concerns that define the space as well. And then, of course, we want to definitely have clear definitions of the metrics involved in explaining a machine learning model, because we want to ensure that it is consistent across all spaces and across all models. And yeah, like I said in the last slide, we want to explore machine learning to explain current machine learning algorithms. And that's about it. Thanks.
Thank you, Rheshav. I do have a question for you when you have time to
No worries.
answer it. And we can move on to Ziwen.
Okay. One moment. I share my screen. Okay, can you hear my screen? Can you hear my screen? Okay. Hello, everyone. Now I want to begin my presentation. Now my presentation includes 4 factors. My research focuses on the application of XAI to traffic accident prediction in modern society. With the development of technology and people's awareness of environmental protection, more and more car companies are changing the directions of development from traditional vehicles to connect to autonomous electric vehicles. CAEV not only facilitates the driver's operations, but also can avoid car accidents through the data collected by sensors. The analysis of the data relies on powerful AI technology. The problem is that despite the powerful of AI technology, people have always chosen not to choose AI for decision, but that can affect their life or safety, but to choose themselves. This is therefore a hindrance to the spread of XAI technology in this subject. I will analyze and summarize the role and the impact of individual AI data analysis model and XAI. I hope this will help the help to promote XAI technology in the field of intelligent transportation. About my finding, I think the traffic accident protection function plays an important role in the driving system, which can provide safety for automotive driver. Traffic accident protection is based on information obtained from image sensors and radar sensors, and the data analyzed model and artificial intelligence and used to make a judgment and decision. Nowadays, with the presence of the intelligent transportation and the development of deep learning, machine learning, the data for protection traffic accidents comes from the measure of self-driving vehicles and road cameras, and the information collected by multiple devices can serve one vehicles. However, traffic accident prediction nowadays also face many problems, such as increasing information collection in low visibility or bad weathers, and the problem of irregular behavior in the absent singles. The solution of these problems mainly relies on building a good data models and provide machine learning with a large amount of data to solve them. This image shows how real world pictures can be understood by machine and analyzed based on this image information to get a useful resource. This method with description machines and the input which in an image and of a cat is fed into a model of processing along the blue line. The result outputs the green singles and the green single, yeah, you can hear, and hence providing information for the intermediately machines of the model in the forms. It has been almost 2 months since the course start, and I'm very grateful Simona for the grading for me during this time. And I have also learned a lot of the from the presentation every Monday. I collect some useful article from 2 academic areas. Firstly, I find some AI technology because I have this knowledge about AI before, so I need to understand the basic knowledge and how far has AI processed. On the other hand, I spend a lot of time on reading traffic accident prediction article and literature. All of the articles were published on recent 5 years. By the time I finish reading all literature, I have a basic understanding of AI technology and traffic accident prediction, which was necessary to complete my final report. During my reading of the report, I completed the literature review. I focus on analyzing the development of XAI and some AI analysis model in recent years. During this time, I will secure the data sources and the data type and compare the idea in different articles to draw my conclusions. I have also completed the abstract and the introduction section of my final articles from these sources. I have some papers about traffic predictions. Most of them are based on the images and make judgments. But what data type to use to make the decision is a different point in these papers. I chose one paper that the analyzer process mentioned in that paper impressed me a lot, and I want to show you that. The article is about the AI-based traffic flow prediction model, and it's published in 2021. The authors think traffic prediction is a significant issue in CAEV area and can be solved by deep learning technology. Deep learning is a well-known and reputed model used in traffic prediction, and the identifications of dependencies in high dimensions data set. So they introduce an AI-based model. The models involves two major processes, feature engineering and the TFP. Moreover, the others consider the support better data description model is utilized to filter the point and smooth the raw data. There are some details of the model of work process flow. The first step is a feature engineering. Please focus on the orange box. There are 3 processes in the feature engineering, but the most significant is the feature selection. which use SVDD to extract or normalize the features. The feature construction is defined as a process in which the required features are extracted from the completed and the actual data site. In case of features construction, a rule established for selecting the data of the type of root section in complex root network. The data side of the situations is such that for the root network, the connection point are incorrectly and should be removed because it contains some intersections of flyovers. And this usually under the traffic control. The raw data, although seems very large, it contains from different sources, and all those data can be merged together. The next step is a traffic flow prediction process. In order to reduce model data and fraction data, the auto extract, associate, and the noise features. The predictions includes these three processes. The first step is computing the predefine the process along with dimensions reduction from the auto input. AE mode is trained to develop the input in output. Therefore, the purpose of training SAE to extract useful features. In the SAF processes, SAE is applied to discuss the computing dimensions by learning spread deception of model data. The authors offer some data to verify its models. This picture shows the performance of the ITFP model. The author said the parameters below and compare it with the other model. According to this picture, we can see this model has the best performance, but we can see the DBN model also have a better performance. But DBN can be redefined a deep belief network in machine learning. A deep belief networking is a generated geography model. This picture shows us that the difference in DBN and the difference in ITFP was only 0.01. And this caught my attention, and I think it could also be used in traffic accident prediction. In the next stage, I will study the article related to this model and to find out its advantages. This table implies a predictive result for the ITFP model by means of a recall under the volume and the speed index. We can see that the model also has the best performance, and the best value results a large difference between the above pictures. This picture can show the result directly. That's all context of this article is offered me massive knowledge and information about the traffic accident prediction. In the next stage, I need to find more articles to get some useful knowledge and support my views. I would like to search for some more data analyze models for predicting traffic accidents. I'm going to look for the reference list from the articles I have been given. Finish others literature reviews also play an essential role in my final report. As I mentioned earlier, I will also next to examine the advantages of DBN data model in the traffic accident prediction, looking for relevant papers, compare the view between the different authors. Also, I look for a factor that affect its performance. Finally, I plan to complete my final report in early October. This reference list. Thank you.
Thank you. Feel free to ask any questions for Ziwen, and Tuo is Wanpeng online, so we can pass on to him.
He's online. Yeah. So next one, Wanpeng, will you share your screen?
Hello, sir. One
Yeah.
second. I need to open my Zoom on my laptop now. Okay.
Okay. Maybe before that, I can share Walden's presentation.
Yeah. 1 second. I need to open my laptop now.
Maybe you'll be the next, and I will share the other one's presentation.
Okay.
Yeah.
That's good. That's good.
Okay. So I'm not sure if it's Let me just. I'm not sure if you can hear the voice or not.
Hi everyone. Today I will be presenting my
Can you? Yeah. Okay. I just leave it on.
midterm update for my honors project, which is traffic accident risk prediction with spatial, temporal, and victim party demographic data. The main focus of today's update will be an overview of the established methodology, which will act as a background to discussion on model development, testing, and evaluation for this project. So to quickly recap, the main aim of the project is to accurately predict the risk level of traffic accidents in city subsections based on spatial, temporal, and victim party demographic data via a deep learning approach, and subsequently evaluate the impact of victim party demographics on accident causation and severity and overall prediction performance. As such, this can be beneficial towards traffic management and emergency services in more effective resource allocation and clearance time reduction. While many past works utilize commonly employed data sources such as historical collision and weather data, our approach integrates additional datasets such as victim demographics, time properties, and road characteristics. For example, the intersection and road network densities within the Los Angeles region, to better model the sparse nature of traffic accidents. Also, the study area used is in Los Angeles from the year 2014 to 2019. To reiterate, the project is separated into 4 key stages. Stage 1 is problem formulation and literature review, although literature review will be ongoing throughout the honors course. Stage 2 is data collection and preparation. Stage 3 is data analysis and insights. And finally, stage 4 includes model development, testing, and evaluation. Stages 1 through to 3 have already been covered, so today's update will primarily focus on the methodology and stage 4, these of which will be covered in the following slides. Now, before discussing stage 4 involving model development, testing, and evaluation, I will summarize the methodology involved as sort of a precursor and background to stage 4. With this in mind, the methodology from a high-level perspective involves 6 steps: feature aggregation, grid separation, application of baseline models for risk prediction, development of proposed model framework, model evaluation and comparison to baseline models, and evaluation of the overall impact of victim and party demographic data. These steps will be detailed in the following slides. The first step is to aggregate the features into 3D tensors of grids with 200 meter, 400 meter, 800 meter, 1 kilometer, 2 kilometer, and 5 kilometer squared size cells to compare sparsity levels. For example, here we can see how intersection density is aggregated. Here, each grid represents the LA district at a certain time step, and in each grid, there are cells which each contain the intersection density value for that specific subsection of the study area. In terms of comparing sparsity levels on different cell sizes, these charts show the total number of specifically non-zero cells which contain a given number of accidents as a percentage of all non-zero cells for the specified cell size. We can see that for 200, 400, and 800 meters squared, the majority of cells largely contain 1 to 50 accidents over the entire time period of 2014 to 2019. However, as the size of the cell increases, we can logically see that the higher accident count cells start to outweigh the low accident count cells. Therefore, the 1 kilometer by 1 kilometer cells, represented as red, indicate the most balanced categories in terms of accident count in any given cell. Further to this, we can see here on the left side that the 1 kilometer by 1 kilometer cell size has just under 85% of all non-zero cells containing 200 accidents or less over the entire 6-year period, which is neither too sparse or too generic. On the right side, where the color intensity represents accident frequency, you can see that 1 kilometer squared also offers the best trade-off visually in terms of granularity in cell count over the entire study area, whereby the total cell count is neither too coarse, as shown in the 5 kilometer squared map, or too fine, as shown in the 200 meter squared map. and is the most optimal geographical division size, given the size of the Los Angeles study area. Now, going back to the overall methodology, the second step is to separate the grid into 3 key subsections to represent major regions of interest within the study area, which will also enable comparison between them. Here, we can see that the 3 sections are separated as follows, with the first upper left region representing the residential area, the middle region representing the downtown area, and the bottom region representing the southmost area. The third step is to apply baseline models such as historical average, SDAE, GSNet, heteroconv-LSTM, and TA-stan over various timeframes for traffic accident risk prediction on project-specific data. Next, we develop a model framework based on the conv-LSTM network to take project-specific data in the form of multiple grid feature layers as input. The input data to the model is in the form of a 4D tensor, with the 4th dimension being the aggregated features, and each input being of length t plus n, where t is a predefined time step, and each time step consists of a number of grid feature layers. Step 5 involves comparing model performance against the baseline models in terms of predictive error. For this, we use 3 key evaluation metrics: root mean squared error, mean absolute percentage error, and symmetric mean absolute percentage error. Finally, we evaluate the overall impact of victim and party demographics on traffic accident risk and severity, and its effect on overall predictive performance by monitoring model performance with and without integrating victim and party demographic data, and whether such data increases in significance in parallel with the nature and frequency of traffic accidents at a given location and/or time. Now, the final stage of the overall roadmap of the project involves model development, testing, and evaluation. With the previous slides in mind, we train a conv-LSTM-based model framework on different timeframes or intervals to find the most optimal arrangement. This, in combination with hyperparameter tuning, optimization, and regularization during model training to incrementally improve predictive performance. During this stage, we will also determine feature importance during model training and on overall performance to reduce the number of feature layers required. In terms of how the data is applied, the entire 6-year dataset and accompanying data is divided into n total sequences, each of length t, depending on the optimum arrangement found. The first half, or specified prior length, of each sequence is used for training, while the second half, or specified future length, is for predictions. In terms of how the data is split, the first 5 years of data are used for training, with 20% of this for validation, and the last year is used for testing. Here, we can see how the process from input to output works, where the input is an unseen sequence of length t on 2, or a specified prior length, for example, prior 14 days, and the output from the trained conv-LSTM network is the predicted traffic accident grids containing the predicted accident locations for the second half or specified future length of the unseen sequence, for example, 1 day into the future. Now, to add on to the previous slide, model training will be undertaken such that each candidate model architecture is trained with all possible combinations of the number of features, number of days prior, and the number of days into the future. For example, a basic autoencoder can be trained with 3 feature layers, with each training sequence consisting of, for example, 14 days prior to predict 1 day into the future. In this way, all candidate model architectures can be compared on all possible combinations of the above. So, in terms of the tasks being undertaken currently, these include establishing historical average baselines for predicting traffic accident risk over different timeframes or intervals, testing various simple model architectures, such as simple autoencoders for initial reference, and testing a standard conv-LSTM network on single features. The next steps will involve applying the model training pipeline, or in other words, the model cycle with baseline models, and the proposed conv-LSTM-based model framework, comparing model performance in terms of predictive area, predictive error over various timeframes, and determining feature importance, which will lead to evaluating the overall impact that victim and party demographic features have on traffic accident risk and its effect on the overall predictive performance. And that's about it for this update. Thank you.
Thank you very much. We just Wanpeng, have you been prepared for the presentation?
Hello, sir. I'm fine. I'm okay now.
Yeah, you can share your screen now.
Okay, 1 second. I share my screen. Here. Okay. Could you see my screen now?
Yeah.
Okay. Hello, everyone. My name is Wanpeng Liu, and my Explore goal is technology development of traffic information monitoring in smart city. Let's see. This is about the technology. It means the GIS is one of the growing applications in the imaging technology field, and it's play a important role in our daily activities and embedded in most of the systems and applications we use today. The technology is used for every activity from weather, traffic navigation, and route mapping to all online delivery applications for ordering food, goods, and other things. It means and help us to understanding the technologies and their promise in the age of automation and digital works. Because the GIS stands for the GIS system, as the map is, of course, a visual representation of quantifiable data. Compared to traditional table maps, a GIS map is dynamic and interactive. It can really previously unseen features by highlighting them and show change of these features over time based on the given attributes. Like see this is the data using the different maps. It is about the landscapes, and every base map scope comparison in different countries. Because for the magic of GIS map layers is that they allow all the staking different types of maps on top of each other on the same screen. This way, different places can instruct and providing much more information. The user can easily toggle between different layers without confusing them. The most basic layer is the so-called GIS base map, like this. Most of the failure with the classical variable base map. Yet, depending on the specific purpose and the type of data can be used as a base map to build each other upon it. Like this is the GIS data types. It has vertical data, point data, line data, polygon data, and raster data. The vector data is the special as data most people are familiar with, as it is format represented in mapping portals such as Open, Street Maps, and Google Maps. It is also used extensively in computing graphics and computer design applications like CAD. It consists of points, lines, and polygons. The point data is typically represent features or distinct data points. Points are zero dimension, so we cannot measure their length of error. Examples of point data would be like cities, points, and interests. The line data is also represent linear features such as rivers, streets, and trails. And the polygon data typically represent areas such as cities, lakes, and forests. The raster data, also known as the grid data, is made of has different values. You also can use typically find raster data on the satellite images and area surveys. Because the smart city is observe a state of environment and activities its citizens to provide better service. The shift to smart cities is expected to bring greater automation, smart routing and traffic, better civilization, and better city management. So in a smart city, everything will be measured in real time and finally by developing sensors, technology, and will play an important role in their integrating large amounts of real-time data, so it can be acted upon on time. It will improve applications ranging from managing environmental quality and the built environment to land use the transportation planning. And this is the GIS. Why the GIS become the central to the smart cities? It has different methods, because in the following research process, I mainly focus on the practical application of GIS data in smart cities. I refer to more real-life smart cities construction cases, learning their lessons and observed exciting results. Like this, they have different methods to work, like collection, processing, communication, and analytics. This is the fourth method of data using in the real world. Collect data, process data, visualize data, and analyze data. The data calculation is the subject, not only the GIS in the wild process. Regardless the field of studying, however, the GIS growing up, the process of data communication become more and more demanding and has been involved into a category of science with methods targeted by collecting data for GIS. And the defined goal is the location-based service. Another smartphone or user based on their applications. The manipulator allows the device to find the position on the map. If the position is wrong, the user can be found and place them into the correct position. A few years ago, this process was incorrect, but now it's better when users help by providing data in order to collect data from it. The geography resolution is another resources from we can find and gather data from it. In future, my goal is important to achieve the project goals, and this will be determined with the help of managers, users, and other stakeholders. We can find the single project because it has multiple goals that we can need to be clearly defined. We also need to collect the data for analyze and process this data. Using this data and to prove our project is okay and analyze the results, because we need to report the results as well. And the final step, I think, it should be the collect the data from the experimental and report the findings in the way, because it's easily understandable by all the stakeholders. This may require creating presentations or reports in the next semester, I think. But for the GIS analysis process, is important for understanding how data can be used to achieve project goals. I think for this a semester, these steps only can be finished by half, because these steps provide a framework for managing and processing data is fully in this subject. And for the next subject, I think we can make it in the real life by some applications. And this is the reference. Thank you for watching. That's all. Any other want to ask some questions?
Thank you very much for your presentation. I think you're the last one, so we can, yeah, if we have some questions, we can ask.
Yeah. I think it's okay. We can stop the recording and then just have like some sort of a free flow discussion with everyone.
Okay.